Every morning, the same thing happens. You wake up inside a story. The faces are clear. The location feels real. Something was at stake. Then you reach for it, and within 10 minutes, sometimes far less, almost all of it is gone. Not faded, gone. The average person forgets roughly 95% of their dreams before they finish breakfast. That number comes from the work of sleep researcher Robert Stickgold at Harvard Medical School, who has spent decades mapping what the brain actually does when the body goes quiet at night. The answer is not what most people assume. The forgetting isn't random. It isn't a flaw in the system. It's the predictable result of something very specific happening inside the brain during sleep, and then very specifically stopping the moment the eyes open. Every night, the brain runs a filing operation. A region called the hippocampus serves as a relay station during waking life, taking new experiences and routing them toward long-term storage. Conversations, faces, locations, the street you walked down this afternoon. All of it passes through the hippocampus before anything gets encoded permanently. During REM sleep, the stage where most vivid dreaming occurs, the hippocampus is still active, still firing, but the chemical environment surrounding it has shifted completely. The neurotransmitters that normally support memory encoding, primarily norepinephrine and serotonin, drop to near zero during REM sleep. Without them present, the hippocampus cannot do what it ordinarily does. The relay station is open. The filing mechanism is switched off. New experiences are still arriving. Nothing is being stored. Neurologist J. Allen Hobson spent decades at Harvard mapping what he called the neurochemical architecture of the sleeping brain. His research showed that REM sleep is flooded with a different neurotransmitter entirely. Acetylcholine drives the visual and narrative machinery that makes dreams feel indistinguishable from waking experience. It generates the rooms and the faces and the logic that almost makes sense, but doesn't quite. But acetylcholine alone is not enough to create a lasting memory. It's like running a projector with no film loaded. The images play. They're vivid, sometimes overwhelming, occasionally more emotionally intense than anything that happened during the actual day. And because the memory encoding chemistry isn't running alongside them, they leave almost no trace. The brain constructs a complete and detailed experience, then produces essentially no record of it having happened. There is a second mechanism operating on top of the first. The transition from sleep into wakefulness is itself a chemical event. As the brain shifts out of REM, norepinephrine surges back into circulation, and the hippocampus comes back online. But it comes back online oriented toward the present moment, not toward the contents of the dream that just ended. The brain's first priority on waking is environmental orientation. Where are you? Is anything wrong? What needs to happen? Dream content is sitting in a short-term buffer when this reorientation begins, and the hippocampus, busy scanning the present, doesn't reach back for it. The window is narrow. Researchers estimate somewhere between 2 and 5 minutes before the buffer clears entirely. After that point, the dream is gone the same way a sound disappears after the room goes silent. Stickgold tested this window directly in a series of controlled lab experiments. He had subjects sleep in a monitored setting and woke them at precise intervals. Some during REM, some at measured intervals after it ended. When woken directly out of REM sleep, recall was high. Subjects could describe dreams in significant detail. When woken 5 minutes after the REM period ended, recall dropped sharply. At 10 minutes, it was close to zero. The same dream that had been fully accessible moments earlier was simply no longer retrievable. He also found that abrupt waking, the kind produced by a loud alarm, accelerated the loss. The sudden neurochemical surge from a jarring wake-up clears the buffer faster than a slow natural return to consciousness. A gradual waking holds the window open too longer. Some people consistently remember their dreams far more than others, and researchers have traced this difference to a specific variation in brain activity. A 2014 study from the Lyon Neuroscience Research Center found that high dream recallers, people who wake most mornings with clear memories of what they dreamed, showed significantly elevated activity in a region called the temporoparietal junction during both sleep and wakefulness. This area is involved in processing attention and self-referential thought. What the data suggested was that high recallers weren't generating more vivid dreams than other sleepers. They were simply waking more briefly and more frequently during or just after REM. Even a 30-second waking, too short to remember in itself, is long enough to allow partial encoding before the chemical window closes. The temporoparietal junction essentially makes the brain more alert to its own internal states. There is also a theory that the forgetting is the entire point. In 1983, Francis Crick and mathematician Graham Mitchison proposed what they called reverse learning. Their argument was that REM sleep exists partly to clear weak or parasitic neural connections from the cortex, running through faulty associations and suppressing them so they don't accumulate and interfere with waking cognition. On this model, remembering the dream would directly undermine what sleep is trying to accomplish. The mechanism isn't failing to preserve the experience. It's succeeding at erasing it. Not every researcher accepted this framework. Critics pointed out that many animals with limited memory consolidation capacity still appear to dream. The debate hasn't fully resolved, but the underlying observation stands. The brain goes to remarkable effort to produce something extraordinarily vivid, and then systematically dismantles any record of it, and that still doesn't have a clean answer. Dream journaling exists to intercept the process at the one moment where interception is possible. Writing immediately on waking, before standing, before checking a screen, before speaking to anyone, forces the hippocampus to encode what it would otherwise release. People who maintain this practice consistently report that recall improves over weeks, not because the dreams themselves change, but because the brain appears to adapt, treating that content as worth preserving rather than discarding. Stickgold described it as conditioning the hippocampus toward a different default behavior. Whether the content is actually worth preserving is a question that has occupied sleep researchers for decades, without a fully settled answer. But the speed of the forgetting, the 2-minute window, the chem-ical switchover, the buffer clearing before most people have crossed the room, all of it points to a brain that made a very deliberate choice about what sleep is actually for. And it made that choice long before anyone.